Okay, cool. Lesson 68, momentum calculations. We will explore how momentum can help us explore collisions. So let's grab a look first at where we've come from to get to this point about using momentum calculation. We started off, if I go backwards a couple of slides, we started off here talking about what momentum is. Momentum is similar to inertia. It's the idea of how much motion something has. And it's a bit of a weird, whereas inertia describes how hard it is to change that motion. So it's similar to velocity, and it's in that it is an idea of how much something's moving, but I said it's got more to do with motion than just how quickly it's changing its place. I sort of tried to do the analogy of the difference between a massive container freighter ship moving at 1 meter per second, 1 meter per minute, versus a snail that moves at 1 meter per minute. Yeah, sure, they've both got the same velocity, but you wouldn't say they have the same motion. Because when you think of a freight, like a massive freighter ship, you're thinking about many more kilograms of mass. So it's kind of like that. That's how I try to tell you guys what momentum is. Momentum is also just about how much. It's just how much of matter you got moving at that speed as well. And that's why their formula for it is P equals m times v. What we then did is we did a couple of quick calculations using different masses. And then we did ones where you had to convert the speed to meters per second. And then we did, the last one we did was just a sort of one where we tried to look at some very subatomic type particles. And that was sort of it for, then we talked about, well, what is the important part about momentum? Momentum is always conserved. And that actually makes it a very easy sort of concept to use. And that's why we use this concept, is momentum is conserved. So velocity isn't conserved. If you think about it, velocity just, you can lose velocity. But momentum, the amount of motion something has will be conserved. That's why when someone talks about, I haven't got the momentum, it's like I haven't got the push force. That's what they're sort of talking about. Now, momentum can be passed from one object to another object, but overall, the momentum at the start and the end must be the same. And because the momentum at the start and the end must be the same, that allows us to do a lot of good calculations. The first calculation I showed you was the sticking collision. I showed you one moving object that slides and collides with another object, like so. What we did then is we said, well, we're going to say the first one was moving at 2 kilograms, we said the second one was 1. We then looked at the total, and we found out at the end of the day that the final speed was slower than the initial speed, because what we did was, I think, remembering P equals P final, which should be said M1 V1 plus M2 V2 equals M3 V3 plus M4 V4. If I didn't do it, then that's just another way you could do it. We've got 2 times 10 plus 1 times 0 equals, whoops, there's not an M4, so I can just get rid of that, equals 3 times, we don't know how fast it's going, so 3 times x. 20 equals 3x. 20 divided by 3 equals x. X equals what? I don't know, like, it's 20 divided by 3 anyway. 6.67. Perfect. So that's how you could do this one. Today we're going to be doing a few more of these types of questions, but we're going to look at what happens if we have different situations. Now, I'm going to sort of pause here for a second just to talk to you guys about a bit of a dilemma that I have with teaching you guys this. So my dilemma with this is that if I grabbed a look at the the curriculum and said, well, what do I have to teach you guys about momentum? And it just says, show you guys momentum in a linear direction. I'm like, well, okay, that's not very useful. And then I had a look at the textbook. The textbook literally explains momentum in one page. And the problem is that I have is that in year 12, you're expected to be able to do a bunch of these calculations with momentum that I'm sure in year 12 physics that you'll be taught. And the other textbook goes through this stuff in a lot more detail. So I was just like, I was really confused. I was like, I don't know if I should teach you guys how to do some of these complicated calculations or not. And so I was in two minds about whether to do it or not, because like the curriculum and the textbook think, no, I don't need to go into it in detail. But the other textbook and year 12 says, yes, you should probably go through detail. So what I've decided to do is this. Today's lesson and the worksheet that goes along with today's lesson, I'm going to teach you today. However, I'm not going to put these types of questions. When I do give you guys a test and an assessment on this, I'm not going to put these types of questions on the assessment. So in that way, this is almost like extra information. You do need to know the basics. You do need to know how to change to calculate a momentum, but you don't necessarily need to know it to this detail that I'm going to teach you guys today. However, I think this should give you guys a good understanding, a better understanding of the power of momentum. And also, it's also not necessarily the most complicated thing in the world, but if you are already getting overwhelmed by dealing with momentum questions, then don't stress yourself too much, because I won't necessarily be assessing you guys on this. Saying that though, next year you'll be expected to be able to perform these calculations. But don't worry, next year Mr. Radford will go back over these formulas anyway for you. So let me go through them now. I've only got 2 examples, but I could do a bunch of different examples with it. But I'm only going to go through 2, and those are sort of going to cover the majority of the different collisions. So the first collision we did was when 2 objects collide and sort of stick together. Let's talk about this one here. I want to talk about what happens when one object collides another object and pushes that second object. So let's watch that again. First object comes in, bumps into that second object, and that second object flies away. And you guys probably have experienced this. Maybe if you've ever played with marbles, you may have seen this. If you've ever played with pool balls, you may have seen this. Like, this happens a lot in pool. You might want to try and get a ball, like if you're trying to get a ball into the corner pocket, you'll hit one ball into it, and then the second ball, once it hits into it, slows down a lot. You may have experienced this in other situations. Maybe bowling, you could maybe draw an analogy of this too. But yeah, the idea is that one thing hits another thing, and then that second thing speeds off really quickly. So hopefully you guys can think of a situation where that might occur. Bowling's a pretty good example, because the bowling ball does slow down a little bit, but as the pins go flying off in random directions. Also bowls, like lawn bowls, many games, like many sports can be sort of described by this, because a lot of sports you try to throw one ball to hit another ball, and that causes it to move. But yeah, like a lot of examples. So here's the question here. Let's go have a look here. Let's say that initially the speed of that first red car was 12 meters per second. We'll just say it was moving at 12 meters per second. And we'll say that the blue car wasn't moving. Let's pretend that for this question, like, let's just analyze it. Let's say we don't know the mass of the blue car. We just know that blue car goes flying off. After the collision, the mass of the yellow car is still the same, obviously, but now it's moving at a slower speed. It's moving at 8 meters per second. Whereas that small blue car, is flying off at 16 meters per second, really quick. Now, what I want you guys to do first, before we even start doing this question, what I'd like you guys to do first is in chat. I want you to make a guess. I want you to try and use your intuition. Okay? We've got a 2 kilogram cart hitting a blue cart, and then that blue cart flies off at a really fast speed, 16 meters per second, whereas the red cart doesn't change its speed very much. I want you to take a guess. Do you think that blue cart has a lower mass than the red cart or a higher mass? And I would like you to write that guess in the chat or say it out loud, up to you. It doesn't matter if you're wrong at the end. It's a 50-50 if you have no idea. I want you to guess, lower or higher. Is it lighter or heavier? I have 4 guesses so far. 5, yeah? Maybe one more. The blue car, the one that flies off, do we think it's a lower mass or a higher mass? Do we think it's lighter or heavier? One more guess, come on. I haven't seen a guess from you, Calvin. I know that you're pretty good at these types of questions, so I want to see a guess from you. Do you think it's lower or higher? Thank you, Imran, as well for your answers, and Leon. Yeah, thank you. Okay, Arvin says the same. That's a good answer too, Alvin. Okay, but generally a lot of people here are thinking it's going to be lower. And I think that sort of makes sense from maybe general experience, is that if you've got, you know, if you throw a brick at I don't know, if you throw a heavy brick at a small fence, well, maybe you throw a heavy brick at it. I don't know, I'm trying to think of something. No, maybe we won't go brick. Maybe we'll go with the bowling analogy. You think about in bowling, you've got a heavy bowling ball that hits a. You think of bowling, you've got a heavy bowling ball that's hitting a light pin. That pin kind of goes flying because it's so light. If it was a heavy pin, probably wouldn't go nearly as quickly. So yeah, it actually makes sense that this blue card is going to be lighter. And the reason we're doing this is because when we get to the end of this question, we're going to check whether our answer makes sense. And in my personal opinion, if the blue card doesn't come out to be lighter, then there's really something weird going on. And it's more likely made a mistake. So how do we do this? How do we actually solve this question? Well, let's do it together. The momentum at the start, the momentum at the start must equal the momentum at the end. Now the momentum at the start is made up of M1 and V1. The momentum at the end is got, give me a sec. I want to make this color coded. So look at this. All color coded. So now let's look at the now let's plug in some values. We know that the red cart is initially moving at, has a mass of 2 and it's moving at 12 meters per second. We know that that blue cart has a mass of, we don't know, in this case it's X, and it's moving at 0 meters per second. Great, so that's going to cancel anyway, so we don't need to worry too much about that one. On the right, we know that it's moving, it's got a mass of X and it's moving at 16. Whereas the mass of the other one, we've got a mass of 2 moving at 8 meters per second. It's still moving forward, so we're still going to use positive 8, but if it was moving backwards, we might be using negative 8. But that's okay. We'll keep this as it is for the moment. So 2 times 12 makes 24. Equals 2 times 8 is 16, plus X times 16 is going to be plus 16X. Okay. If I minus 16 from both sides to cancel out. If I minus 16 from both sides, that's going to give me 8 equals 16x, which means that essentially if you divide both sides by 16, hopefully you guys are happy with this. X equals 0.5 kilograms. And that's after being simplified. You could just write a half, that's fine too. And so that turns out that that's lighter. And that's again what we were thinking that it would be. It would be lighter, it would be a lighter mass. And so that's our good check at the end, just to see if this makes sense. So let's go through what I did to solve this. So the amount of momentum at the start and the end must be the same. So our initial momentum can be calculated by taking the momentum of this, we'll add it to the momentum of this. The momentum of this is 0, because it's not moving. The momentum of this is 2 times 12 is 24. That's how we got the momentum on this side is 24. That means the momentum of this whole thing must be 24. So if we know 2 times 8 is 16, then whatever times 16 added must be 24 kilogram meters per second. So that's how this sort of question was done. Now again, as I said, you're not really you're not really expected to be able to do a question like this for some reason, but I'm not 100% sure. It's one of those ones I'm going to have to double check with teachers. I think a lot of teachers would be teaching this to their year 11 students, trying to prepare them for year 12. So I thought I would show you guys anyway. You're going to have to do similar types of questions to this anyway when we do energy. So it makes sense to start talking about it now. Are there any questions on this stuff? Or because I've got one more example that I want to do with you. But if there are questions or queries, then I will go through them now. Okay. All right, that was 15 seconds. I'm going to assume that there's no issues. So I'm going to move on. We're going to do one more example with momentum. And that last example of momentum is going to be this one here. In this case, we've got a 6 kilogram object. Now, 6 kilogram object, and I've tried to increase the size of this little cart to sort of show you that it's a bit heavier. So now what happens is our red cart flies along, hits into that 6 kilogram object, and you can see in this example, the 6 kilogram object starts moving forwards at a pretty slow rate, but it's still moving forwards. But that red one moves backwards instead. You might have seen something like this if you were to imagine if you were to roll a, if you imagine if you're throwing a ball against a heavy cart, maybe even a bicycle, the ball might go backwards. Or if you throw a ball at a shopping trolley, yeah, sure, the shopping trolley might move forwards at a slow speed, but that ball that you threw at the shopping cart is going to fly backwards. It's going to come backwards towards you. It's not going to keep going forwards. And there are other examples where this might occur. So, like, what's going on in this situation? Let's start to analyze this. I would refer to this as a bit more of a bouncing thing. And it kind of makes sense as well because that mass of that initial cart was 6 kilograms. It's a pretty heavy cart. It sort of makes sense that, instead of pushing that and still going forwards, that red cart pushes that and actually starts moving backwards. So let's have a look here to see, well, what situation could be occurring this. We're going to look at, so we've got here a 2 kilogram cart. We're going to say that 2 kilogram cart, we're going to calculate the velocity this time. We're going to say that initially it's traveling at X meters per second. And that 6 kilogram cart is not moving. I will point out that with a lot of these calculations, I've said that first cart is not moving. You could do these calculations if that first cart was moving. That is completely fine. And the equations would turn out just the same. at the end afterwards, that card is still that red card bounces and starts moving backwards at 2 meters per second, whereas that blue card is moving forwards at a pretty slow speed. So here's going to be my first question for you guys, and I want you guys to try and use your intuition in chat, and you don't have to get this right. That's completely fine if you get it wrong. Do you think this red card, do you think it's going faster than 2 meters per second? When it goes forward, do you think it bounces back at like, do you think it's going forwards at 1 meters per second and then it bounces back and it's traveling 2 meters per second? Or do you think maybe it's traveling at 2 meters per second and bounces back at 2 meters per second? Do you think it's going faster than it's slowing down? What do you guys think? Okay. Wow, cool. Thank you so much. And Kelvin, first off the mark for this guess. We've got 4 guesses straight away. People saying faster. Initially, they think that red card is going faster, and then it hits and then it slows down. Anyone else got a guess? Does anyone think slower, or is most people thinking faster? What about you, Phoenix? What do you think? I haven't seen your, or Imran, I haven't seen your, you responded last time. Do you think it's fast, that at the start, do you think it's going faster or slower than 2 meters per second? Just take a guess. It could be wrong because we haven't even done any calculations. Imran saying faster too. Okay, cool. Thank you, Imran. I appreciate that. So yeah, let's explore this. The reason I think this is good is because it's testing your own intuition. You're trying to explore it. You're trying to. We'd really like you guys to try and think of an example where you might have tried this out. If any of you guys have got little brothers and sisters that have toys, a lot of toys, like a lot of moving carts, even if you think about that, like, I don't know, the little one with the xylophone on it, the little piano that you hit, you know, that's got wheels. If you imagine that, try and hit that with a ball and just imagine what happens to the ball goes flying backwards, whereas the cart might move a little bit. So let's have a look and see what's going on here. Well, our initial momentum is going to be equal to our final momentum. In this case, our initial momentum here is going to be m1 v1 plus m1 m2 v2 equals, in this case, m3 v3 plus m4 v4. And if you had more objects, by the way, you would just add them on, but usually you're only going to have 2 objects interacting. So let's look at this. We've got 2 times x to be our first one, so 2x plus 6 times 0 equals, in this case we've got 2 times negative 2. And here we go. This is important because this is going in the opposite direction of the initial, which we're going to call this a negative, plus 6 times 2. We need to make sure this is a negative because ultimately, if they were moving in the same, if they were had the same velocity, if they both had 2, then they would be stuck together. And that would actually change the question a lot. But that means that our final, when we finally calculate this, 6 times 0 is going to be 0. So we've got 2x equals 2 times negative 2 is going to be negative 4 plus 12. Now you can then calculate that to be, so if we then work this out, that's going to become 8. 2x equals 8. X equals 4. Plus, that tells us it's a positive. So that means it's 4x equals 4 meters per second to the right. And that's how we can use this to calculate this one. It's pretty much the same example as the previous one. The only addition that I wanted you guys to think about is negative 2. You guys that said faster, you were right. It was initially going 4 meters per second. At the end, it's going 2 meters per second. That's a change in velocity of 6 meters per second. because you're going from 4 down to -2. That's a pretty big change in speed. That change in speed might be caused by some kind of force, because a change caused by some kind of acceleration, which is a force. All accelerations must be caused by a force. So, and that's actually what we're going to explore next lesson. Next lesson, we're going to talk about, well, what was that force that made that change? But let me just do one last thing. One last thing before we move on. I want to look at this from a different lens, a different perspective. Okay, what am I going to do? What I'm going to do is I'm going to switch to purple because I want to use a different color. We know X now. We know that's going to be 4. So let's look at this. P equals mv equals 2 times 4, which is going to be 8 kilogram meters per second. But at the end, we've got 2 times 2. So P equals 2 times 2 equals negative, we've got negative, well, that's because that's in a negative direction. So we've got negative 4 kilogram meters per second. Now what I want you guys to look at is we've lost a lot of momentum. We've actually lost 8 plus 4. We've actually lost 12 kilogram meters per second because it's gone from 8 down to -4. We've lost, this red card has lost 12 kilogram meters per second. Whereas this blue card started with 0 and then is finishing up at 2 times 6. T equals 2 times 6, which is 12. So the blue card gains 12 kilogram meters per second. And that's why you know that it's conserved. That's how you know that the whole thing is conserved. The amount that the amount of momentum the red card lost was equal to the amount of momentum the blue card gained. And you could actually create a scenario as well where that red card just stops moving and that red card transfers all of its momentum to that blue card, which goes flying off at some crazy speed. Oh, by the way, in the top right hand corner, when I first made this question, I had the red card bouncing back at 4 meters per second. And although you could do the momentum calculations, you could figure out the initial speed, it didn't work anymore because what I had accidentally done is I violated the conservation of energy law. And that actually still has to apply even though we're talking about momentum. We haven't talked about what that law is that I violated yet because we're probably not going to get up to that law until probably either Friday or next week. So yeah, but later on what we might do is we might come back to this example again later on and look at this from a third lens, looking at this from an energy lens. How much energy does that red card have at the start and how much energy does that red card have at the end? And if those are not the same, then where is that energy going? That's just a different way we can look